Hello and welcome to our final project on diffusion models. Let's start off with some background and motivation. So first, a diffusion model has a couple primary components. First is the forward process, where we take a sample and add random noise. This is often very easy, and it ends up at the end getting to be completely random noise. Then there's also the reverse process, where we can take a noisy sample and attempt to take it back continuously back in time to back to the target distribution. This is often quite difficult, and this is where the bulk of our presentation, what it'll be about. What can diffusion models be used for? They can be used for image generation, protein generation, computer vision, natural language processing, and really anywhere else where you want to use a generative model. These are useful because they can outperform oftentimes other generative models that are use generative adversarial networks. This has been shown by Nickel in 2021. And one of the key benefits is that it does not involve adversarial training. Here's sort of what we're going to be covering today. Forward and reverse PDE representations of probability distributions, along with reversing the SDEs. And then we'll cover a couple of key denoising approaches. And then we'll talk about how to train the score network, discretizing, visualizing this process. And then the last quarter will be about applications. So most of the key theory behind this technique comes from Anderson in 1982, who did a lot of stochastic calculus that allows us to do this. He found that given a forward time SDE, we can create a reverse time SDE. This is from Kolmogorov. So we first create partial differential equations describing probability distributions. This is akin to what we have in our class notes. We have the Fokker-Planck-Kolmogorov equation, which is shown here. It can be thought of as akin to the advection diffusion equation. So we have a drift term and a diffusion term. Then we also have the backwards equation. This one's a little bit more interesting. We assume that we know what the distribution is at some prior time, little t, and then it's looking at the distribution, the posterior distribution at a later time, big T. But this is less useful, and this is where Anderson comes in, because he looks at the joint probability distribution for a time s and another time t, and then does a lot of computations, and then we will end up with an SDE that we can use. So I'll give a brief sketch of the proof for this. We first take the joint distribution, apply Bayes' rule, and then multiply by -1 and apply, take the partial derivative with respect to t, and the product rule, and out pops two terms that look quite familiar from the previous slide. We get the backward and forward Kolmogorov equation. So we obviously plug these in. It looks kind of ugly. We do a lot of little tricks with algebra and differential calculus, such as completing the square. And we end up with what I have here in the middle. Then you can marginalize over the future time s and get what follows at the bottom. So we have that here. And then the last couple of tricks are to introduce a time reversal, which will give an SDE that looks like the forward Kolmogorov equation. And this can then be solved backwards in time. And then the final SDE result is shown here at the bottom.
So I'm going to talk a little bit now about different ways of denoising the prior distribution, so we can go back from our Gaussian noise and actually generate samples from the original data distribution. So there are several classical discrete ways of doing this that I'm going to talk about, and then I'm going to talk about how they generalize when we take the step size limit to 0, how they become, a continuous reverse SDE, which we actually know how to deal with and we just saw. So for now, I'm going to assume that this score function, which is, in practice not really recoverable, I'm going to assume that we've estimated it, perhaps with a deep neural network or something like that. And throughout, I'm going to use the language of sampling and sampling algorithms, but there is a direct bijection in between denoisers and samplers. So one of the models that's been proposed and received a lot of attention is called denoising diffusion probabilistic models, or DDPM. And just as the name suggests, it's a denoiser, and basically the way it does that is by training a set of probabilistic models at each of a discrete set of noise scales. So for each set, we can define, to go forward, a Markov chain that sets the marginal probability conditional on the previous state. But once we've done our score estimation, we end up with something like this, which is our estimated score, and we can actually then reverse the Markov chain in order to sample backwards in time. And so this technique is often called ancestral sampling because we're starting at the child nodes of the Markov chain and propagating back in time towards the original data distribution. So a similar but slightly different technique to DDPM is called score matching with Langevin dynamics, or SMLD. And so what SMLD does is it defines first a sequence of increasing noise scales and then uses those to perturb the data with a Gaussian kernel, and then you sample backwards using Langevin Markov chain Monte Carlo, starting with the largest noise scale and then moving back in time towards the beginning. So a natural question is, how do we think about these in the limit when we take the step size to 0? And it turns out, and we derive this in the appendix, that they both approach SDEs that are very easy to write down and very easy to understand and solve, but they're very different from one another. So DDPM, you end up with something that looks a little bit like this, that's not too hard to think about. And SMLD approaches this SDE that first of all has no drift term, it's just a pure martingale, but second of all has this variance that explodes. Whereas DDPM, you end up with this bounded variance here, and you can see also, if the blue line is the SDE, then the discretization matches it quite well, which as we would expect. So if we continue with the SDE for DDPM, we can just think about, we have this forward SDE that we understand and we can write down, but we know from the beginning that we can then write down some reverse SDE. So we can take a sample of random noise and use it to create a representative sample of our original data distribution. So we can create, new images, new molecules, things like that. And it can actually be decomposed into this first term that we might call the probability flow ODE. There's no stochasticity there. And then this second term, which is a Langevin diffusion SDE. And so a natural enough question is, what is this probability flow thing doing? And it turns out that it actually has a very interesting and important interpretation. So the probability flow ODE, you can show that for any of these reverse SDEs, then there's actually an ODE that has the same marginal probability distribution as the original SDE. And so this is often called the probability flow ODE because it's just an ODE that describes how the probability flows between the prior and the data distribution. And so this is really useful because it means that we can make a choice between whether we want to model the reverse process using the actual full reverse diffusion or just using an ODE. And so this means you can make, a choice based on, whatever constraints your problem has between using a stochastic, numerical simulation like Euler-Maruyama, or if you want to do it deterministically using something like, Euler, Runge-Kutta, and there's, lots of options out there. So all of these models can be generalized slightly into this notion of this sort of Hamiltonian Langevin mechanics. And so it's been proposed that all of the previous techniques I've talked about actually correspond to this high friction, over-damped Langevin dynamics. And that leads to slower convergence than we would like. And so it's been proposed that if instead of injecting the noise directly into the data distribution, if you add on this velocity component, and you end up with these, sort of Hamiltonian mechanics, if you inject the noise into the velocity, then you can actually get substantially better results. And that is done in part by getting on the critically damped, so the sort of the threshold between overdamped and underdamped Langevin dynamics, by setting this gamma, this friction term, in an appropriate way next to this mass. It's a hyperparameter. And so you can decompose that into this Hamiltonian component that you can simulate using whatever your favorite simulator is, and then this Ornstein-Uhlenbeck process that we already know how to solve.
So in a previous section, we learned a couple of different approaches that can be used to take some noisy data and convert it into samples from our original probability distribution. And in a couple of these cases, particularly the noise conditional score matching and reverse SDE denoising approaches, we need access to this score function, which is given by the gradient of the log of the probability distribution in order to do this reverse process. And since we don't know the original probability distribution, we aren't able to retrieve the score function exactly. So we need to use a neural network to approximate it. And this is, in most cases, the main source of error for diffusion models, unlike something like normalizing flows, in which case the tricky part is choosing the forward and backward processes. So for the case of the reverse SDE, we can write the loss function for the neural network as shown here. And this is just a time average of the distance between our approximate score function and the true score function. And the reason why we need to do the time average is that in the definition of the reverse SDE, we need a time-dependent score function, not just the noiseless score function. Then a key result from Vincent in 2011 showed that we can rewrite this loss function in terms of the conditional probabilities, as shown here. And this is a very important result because as written originally, it's not clear how we can go about maximizing this loss function or minimizing this loss function because we don't know what the probability distribution is, and therefore we don't know this gradient log p term. However, in the case in the bottom, since we chose the forward process, we actually can calculate the gradient of log of p of x of t given x0 directly, depending on our choice of f for the forward process. So over here on the right, I have a couple of images which just show what the forward process might look like if the data is an image. So it basically just looks like a Gaussian blur where we start with some very clear image and we slowly distort it into closer and closer to noise. So now that we have the score function, we want to actually sample from the reverse SDE. And to do this, first we'll look at these two equations for the forward and reverse SDE, which we saw earlier in this presentation. And it is very typical to choose an Ornstein-Uhlenbeck process for the forward process, which is the case when f is a scaled version of negative x, and g can just be 1 because it's equivalent over a time change. And if we make this choice, we can explicitly calculate the probability distribution of the forward process in terms of the original probability distribution, like we did in a homework problem as shown here. And the important thing to note is that as time approaches infinity, this distribution approaches a mean zero Gaussian, which is very easy to sample from. So now, when we actually want to do the reverse sampling, we need to discretize the reverse process. And one important detail is that when we have this reverse process shown here, we're able to only discretize the score function and keep the continuous dynamics of the first term. And the derivation for this is shown here, but it looks very similar to a lot of the calculations we've done this semester, where we set up some other stochastic process in terms of our original and apply Ito's formula. But this is actually very important because it allows us to make a more accurate representation of the backwards process. So now I want to give a quick visualization of what this reverse SDE might look like. So in this case, our data distribution is just a distribution of points in R2, and the true distribution is shown in this image on the left. And over here on the right, we can see the backward process in action. So at the beginning, at capital T equals 0, we start from just random Gaussian noise. And slowly, as we get to higher times, we get closer and closer to our original distribution. And as you can see, by the end, it looks very similar.
Now that we've covered the underpinnings of diffusion models and strategies to denoise them, we take a look at select connections and applications. First, we look at combining diffusion probabilistic models with normalizing flows in a paper titled Diffusion Normalizing Flows. Second, we look at conditional generation with score-based diffusion models, as well as conditioning strategies in practice. Finally, we look at some applications of usually conditional diffusion, observing it for tasks like text-to-image generation and graph generation in the molecular sciences. Diffusion normalizing flows is a concept introduced in 2021, which essentially, by a certain choice of coefficients, mixes normalizing flows and diffusion probabilistic models. As you can see in this diagram, in normalizing flows, you have a function that's invertible, and you have a forward and a backward step between time steps, while for diffusion models, we have a set diffusion process that moves forward, and we are learning the backward process. While for diffusion normalizing flows, there is a stochastic differential equation that looks very similar to what it would be for a diffusion probabilistic model, except that there's a learnable drift term. And what's interesting is that such models can learn distributions with sharp boundaries, unlike normalizing flow, but they use fewer discretization steps with better sampling efficiency than diffusion probabilistic models. Conditional generation with score-based diffusion models is essentially built on the same forward process. However, if there's something we'd like to condition on, let's say an object like an image or a piece of text, the backward diffusion process can be modified by replacing p sub t of x sub t, but with p sub t of x sub t conditioned on y. And so it's really quite a simple thing, but it's very powerful because learning the conditional score function enables sampling from the now conditional prior. And this is a concept that was explored at length in 2021 paper. Conditioning strategies in practice usually take one of three guidance forms. The first, introduced in 2021, is classifier guidance, where the diffusion score is modified to include the gradient of the logarithmic likelihood of a helper classifier model. And so you can imagine how training an auxiliary model might not be ideal. And so in 2021, a classifier-free guidance system was also introduced, whereby there's a joint training of unconditional and conditional models by randomly setting the conditioning to an unconditional state with a certain probability, and then sampling is performed using a linear combination of conditional and unconditional score estimates, where choosing a parameter of 1 devolves into unconditional generation, but increasing that parameter results in stronger classifier-free guidance. Finally, a third form of guidance that's somewhat popular is clip guidance, where you train a contrastive learning loss with a function that is supposed to match objects like images and their respective captions together, and contrast that against other images and other captions that do not match. CLIP was introduced by OpenAI in 2021, and CLIP guidance for diffusion models was introduced also by OpenAI in 2022. Text-to-image generation has become a very popular application of diffusion models. DALL-E 2, introduced in 2022, uses clip latents that are frozen and then performs the denoising diffusion model. And Imagen uses classifier-free guidance. This is a model from Google and from 2022 that has a frozen text encoder and performs a base UNet diffusion, as well as several super resoluting UNet diffusions to increase image quality. Generation on graphs was summarized in a good way in a 2023 review that pointed out the use of all three frames of diffusion models, such as score matching with Langevin dynamics, denoising diffusion probabilistic models, and score-based generative modeling for tasks such as molecule conformer generation, molecular docking, protein generation, and protein ligand structure prediction. In particular, we'd like to highlight two examples: equivariant diffusion for molecule generation in 3D. You can see you start with a cluster of points that are essentially Gaussian noise, and this can be denoised into a fully formed molecule. Another example is RF diffusion for proteins, which also takes essentially a cloud of Gaussian noise and diffuses it with some structural guidance into a appropriate protein or peptide for binding. We'd like to conclude by reminding you that we've covered the 3 types of diffusion models: denoising diffusion probabilistic models, score matching with longevity dynamics, and score-based generative models, as well as connections to normalizing flows and applications in text-to-image generation and molecular sciences. Finally, we would like to express our sincere gratitude to Professor Mattingly for teaching stochastic calculus this semester. Thank you.